I am an engineer. I find beauty in modern power stations and the pylons and wires that stretch over the face of Britain. I'm proud, too, of the fact that per head of the population, Britain has a greater mileage of cable than any other country in the world.
I'm the man in the street. I think of electricity as revolutionizing old customs and habits on the farm, in the factory, and in the home.
But as an engineer, let me remind you that for all these purposes, a different cable is necessary, from the supertension oil or gas-filled cable bringing power to a city, to the simple piece of flex bringing light to a reading lamp. Today, whether the generating station is to supply a manufacturing town, a housing estate, or a rural area, we must first plan where the cable shall be laid and determine the course of the main arteries which are to carry electric power to the members of the community.
And here they are, laying one of the ever-growing networks of cables and wires which travel beneath the street or over the fields, and sometimes beneath the waters of rivers, lakes, and seas, bringing heat, light, power, and communications to every house, office, factory, theater, cinema, farm, and village. What romance lies there in those tunnels underneath the streets on which we walk?
This is a cross-section of the main cable. The copper conductors in the center are the paths along which immense power passes. The other layers, impregnated paper insulation, lead sheath, armoring, and outer covering are for insulation and protection purposes. The copper from which the wire is made, in vast quantities, comes mainly from Rhodesia, and in the form received is known as blister copper. The blister copper is melted and refined in the furnace, the temperature attained being approximately 2,100 degrees Fahrenheit. This crane, operated with great skill by its driver, loads the copper into the furnace. The charge amounts to about 200 tons. Is that a picture?
It certainly is.
After the copper has been melted, the refining operation is commenced. Air is blown into the molten metal to oxidize the impurities. These are formed into slag, which is frequently skimmed from the surface of the metal bar. Finally, green trees are forced into the molten metal to reduce the copper oxide formed during refining. This operation is known as poling.
In the same way as eggshells make soup clear, I take it.
It takes about 24 hours to complete the melting and refining operations and bring the metal to the correct condition for tapping. The molten copper is cast into wire bars in these molds, which are made to move automatically so that there is no break in the pouring.
Like coffee cups on a quick service counter.
As the molds leave the lips of the ladle, they travel slowly down until they get to the point where they're automatically tipped. The wire bars are dumped into the water. From there, they're automatically conveyed to an inspection table. Pneumatic hoists lift them into trucks which carry them to the rolling mill, where they're reheated until they're red hot prior to rolling. The wire bars are then reduced to quarter-inch rod by passing at great speed through a series of grooved rolls.
You just can't describe the effect in words. Let the music do it. what's happening now?
This is the black rod being lowered into an acid bath to be pickled to remove scale and oxide, emerging copper red. It now goes to the wire drawing plant, where it is first drawn down on these machines, carrying dies of decreasing diameter to small dimensions. Similar machines with diamond dies draw wires to even smaller sizes. This wire is finer than a human hair. Now the larger wires are stranded to form cores of various sizes.
It's good to find occasionally, among so much that's ugly in industry, a manufacturing process such as this that looks so fascinating.
A most important process is the insulating, to enable the cable to hold the electricity within the conductor. For this purpose, layers of specially treated paper are lapped over the copper. If you look closely, you will see that this particular cable is not round, but oval-shaped. In a moment, we shall see the reason for this. Here, for instance, is a 4-core low-tension cable. The reason for the oval shape becomes apparent. It enables the cores forming the cable to lie snugly together without causing internal stresses. This high-tension cable has 3 cores and is assembled in the same way. The cores are neatly drawn together and taped. As the cable comes off this machine, it is wound directly onto a cable drum. The cable now goes into the impregnator to undergo a vacuum drying and impregnating process. This will take as long as a week. Let us look at some of the various types of wire undergoing other processes. Some wires are insulated with rubber. The wire is first tinned with a special tin alloy designed to preserve the insulation and facilitate soldering of joints. The rubber is first warmed and mixed through one pair of rollers. It then passes through a number of other rollers, which reduce it to the required thickness. This process is known as calendering. Some cables for special purposes, for instance cable for industrial plant and mines which need extra toughness, have rubber lapped onto them. Other wires for household purposes have rubber rolled onto them between grooved rollers. 3 layers of rubber can be distinguished here: white, black, and white. The longitudinal joints are sealed automatically as they are cut. Some wires are covered with rubber by the extrusion process. In all of these processes, the rubber is finally vulcanized. But rubber is not the only insulating agent. Plastics can also fulfill many of the functions of rubber in the insulation of this type of wire and cable. These are prepared in a similar way to rubber. The plastic is warmed and mixed and then calendered. Now it is extruded or squirted onto the wire to form a tough, hard-wearing insulation. This plastic-covered cable is braided with wire. It is to be used for high-frequency radio purposes. Another black plastic outer covering is extruded onto it before it is finally completed. Many fine wires are braided on these ingenious machines.
Isn't that like the way they knit stockings?
Yes, and the use of this wire is still a war secret.
And this looks like a maypole.
Yes, its flexibility allows it to be used for many household purposes. The power cable we left in the impregnator has had every vestige of moisture removed and has been filled with oil. It is now going to the lead extrusion press. It passes through this press, where it receives a sheath of lead, is cooled by water, and then wound directly onto the cable drum. The lead makes it completely waterproof. But the lead itself must be protected from damage, so the cable passes through a further machine where it receives first a bituminous compound covering, then coverings of paper and hessian, or jute, as a bedding for the wire armor. The wire armoring receives a further covering of compound and hessian, or jute, and a final covering of whitewash to prevent it sticking on the drum. And so, the care with which all these coverings are applied protects the public against any possibility of breakdown in service. Copper for high conductivity, paper insulation to confine the immense power to the conductor, lead sheath for protection against moisture, armoring against mechanical damage, and a further outer protection. But still, scientists in the laboratory, having at their disposal the most advanced apparatus, are continually improving existing material and experimenting in the use of cable for new purposes. Let us watch for a moment this power cable that has received a new type of insulation. It is about to undergo a destruction test. This particular cable is designed to carry approximately 30,000 volts, but the voltage passed through it in this test goes up and up. Here we are at 30,000 volts, 100,000 volts. The cable still holds. 300,000 volts, 400,000 volts. It fails. At 400,000 volts, for a cable designed to take only 30,000 volts. The cable at this point of failure is carefully dissected. First, the sheathing is removed, and then the paper tapes are removed. These tapes are then impregnated with a special magenta dye, which enables the pattern of the breakdown to be traced out. This pattern can be read by the experts to give them the clue to the reason for the test breakdown.
Planning and reconstruction are in the minds of us all. We are thinking of the full application of electric power. Cables like this are being laid all day, every day, throughout the British Empire and in all the countries of the world. A cable like this, no thicker than a man's wrist, is capable of harnessing 140,000 horsepower. Power for business, education, light for shops and homes, power for factories, power for transport and communications, power, in fact, to benefit all in health, work, and play. Things electricity can give through cables to Britain and the world.